Today we are going to study a process scheduling and time. In this part, the concepts are a process scheduling, system call for time and a clock. So what is a process scheduling? So on a time sharing system, the kernel allocates CPU to a process for a time slice or quantum preempts the process and schedules another when one time slice expires and reschedules the process to continue the execution at a later time. See one example. Suppose there are five questions in your examination and time slot is given as a 2 hours to solve this question. Suppose the question have equally marks. Suppose this is a question first, question second, question third, question fourth, and question fifth. So each question have equally marks. Suppose marks is equal to 10. This is question first, second, third, fourth, fifth, and total time for solving all these questions are 2 hours. That is 120 minutes. And so for these questions, you have allocated in first time slot is 10 minutes to each question. Suppose you have started to solve question first and within 10 minutes you have solved up to this part question first, then you stop and in next time slot next 10 minutes you have taken a next question second, and within that time slot you solve this question up to this part, then next 10 minutes a time slot you have solved the question like up to this, then next time slot you have solved the question fourth up to this, Then next a time slot you solve this question. After this, this is a first a time slot is given to each question. This is a T1. Suppose next a time slot again you are allocated to each question is 10 minutes. Second time slot, so 10 minutes. So question first, these are the question first, second, third, fourth, fifth. So during a second time slot, question first is solved. Suppose up to this part, then question second will be solved during this time up to this. Then during next time slot, question third will be solved up to this. Then question fourth will be solved during next time slot. Suppose up to this. Then during next time slot, question fifth will be solved. Suppose a whole question is completed. Then next a time slot third question first will be solved for 4 minutes. Next remaining time slot for question first during question 4 minutes it is solved up to this. Question first is completed. Then during next 4 minutes question 2 is solved. Suppose up to this. During next 4 minutes time slot question third is completed up to this. Then during next 4 minutes time slot, out of them within 1 minute question 4 is completed. So remaining time slot is given to question second or question third as per requirement. Then fifth remaining time slot for question fifth is already completed. This 4 minutes time slot slice is given to question second or question 4 as per requirement. This is a scheduling for, that is a time slicing or round robin scheduling. So on a time sharing system, kernel allocates a CPU to a process for a period a time called as time slice or time quantum, preempts the process and schedules another one when the time slice expires and reschedules the process to continue execution at a time later or at a later time. The scheduler function of a Unix system uses a relative time of execution as a parameter to determine which process to schedule next. Every active process has a scheduling priority. The kernel switches context to that of process with the highest priority, and when it does the context switch, the kernel recalculates the priority of running process. When it returns from kernel mode to user mode, and it periodically readjust the priority of every ready to run process in the user mode. Some user processes also have need to know about the time. Some user processes also have to need to know about a time. For example, time command prints the time it took for another command to execute, and the date command prints the date and time of the day. So various time related command we have seen in practical session, the time related commands such as calendar, then date and time. So these are the time related system calls allow process to set or retrieve kernel time values or to ascertain the amount of process CPU uses. The system keeps time with the hardware clock that interrupt the CPU at a fixed hardware dependent rate, typically between 50 and 100 times a second. Each occurrence of the clock interrupt, each occurrence of the clock interrupt is called clock tick. So the concept explores a time-related activities on the Unix system call, considering a process scheduling, system call for time, and the functions of the clock interrupt handler. You have seen in Unix, you have seen in operating system concept, that is a process scheduling concepts, that is round robin, also known as a time slicing. Then you have studied shortest job first, that and SRTN shortest remaining time next. Same, the scheduler on Unix system belongs to the general class of operating system schedulers known as round robin with multi-level feedback, meaning that the kernel allocates the CPU to a process for a time quantum, preempts a process that exceeds its time quantum, and feeds it back to into one of several priority queues. A process may need many iterations through the feedback loop before it finishes. When the kernel does the context switch and restores the context of a process, the process resumes execution from the point where it had been suspended. So this is the algorithm for process scheduling. For this algorithm, there is input none, output also none, while you should have to check no process picked up to execute. If it is a true, then check for every process on run queue or not. If every process is on run queue, then pick the highest priority process that is loaded in the memory. And if no process eligible to execute, then machine goes to the ideal state. So then remove the selected process from the run queue, switch the context to that of selected process and resume its execution. The kernel executes this algorithm through scheduler flags, selecting highest priority process from the those in the state are ready to run and loaded in the memory and preempted. It makes no sense to select the process if it is not loaded in the memory, and since it cannot execute until it spawned in. If several processes tie for highest priority, if several processes tie for highest priority, kernel picks the one that has been ready to run for the longest time. Following a round robin scheduling policy, if there are no processes eligible for execution, if there are no processes eligible for execution, the processor goes to the ideal state until next interrupt, which will happen at most one clock tick. After handling that interrupt, kernel again attempts a scheduling process to run or execute that process. This is the algorithm for process scheduling. See, this is a range for process priorities. In this figure, there are two modes: kernel modes priorities and user modes priority. In kernel modes priority, in kernel mode priority and user mode priority, between these priorities, there is a threshold priority which divides these kernel mode priorities and user mode priorities. So in user level or user mode priorities, there are levels from 0 to n. Similarly, in kernel mode priorities, there is allocation of different input output devices or buffer allocation or inode allocation, or some processes go to the swapping mode. So these are the priority levels, that such as for kernel mode priorities, swapper waiting for IO device, waiting for buffer, waiting for inode, or waiting for TTY input, that is a text to terminal input, waiting for TTY output, and waiting for a child exit. These are the priority levels in user modes. Then there are different levels to user level 0, user level 1 to user level n. And for right side, these are the different processes. See in this figure, each process table entry contains a priority field for process scheduling. The priority of a process in user mode is a function of its recent CPU uses, with processes getting a lower priority if they have recently used the CPU. The priority of process in user mode so each process table entry contains a priority field for process scheduling. The priority of a process in user mode is a function of its recent CPU uses, with process getting a lower priority if they have recently used the CPU. The range of a process priorities can be partitioned into two classes as shown in this figure. There are two parts: kernel mode priorities and threshold mode, user mode priorities. And these two parts are separated by a threshold priority, and each class contains a several priority values, and each priority has a queue of processes logically associated with it. So this figure shows the threshold priority between user priority and the kernel priority. This figure shows the threshold priority between user priority and kernel priority. This is the threshold priority seen in this figure, and threshold priority is set between two priorities: kernel mode priority and user mode priority. This double line indicates a waiting for child exit and user level. This is the double line between waiting for child exit and user level. This is the threshold priority. The priority called swapper, waiting for disk IO in kernel mode priorities. Priorities are swapper, waiting for disk IO, waiting for buffer, and waiting for inode are the high non-interruptible priorities with 1, 3, and 2, with 1, 3, and 2, and 1. These are the processes. Swapper have 3 processes. Waiting for IO disk have 3 processes. Waiting for buffer 2 processes. Waiting for inode is 1 process. Are queued on respective priority level, and the priority is called as waiting for TTY input, TTY output, and waiting for child exit. So waiting for TTY input, there are 4 processes. Waiting for TTY output, there are 0 processes, and waiting for child exit, there are 2 processes queued respectively. So this figure distinguishes user priorities called from user level 0, user level 1 to user level n, containing the priorities 0 for user level 0, then 4 for user level 1, and 1 for user level n respectively. The kernel calculates the priority of a process in specific process state. See this figure carefully. The processes with user level priorities were preempted on their return from the kernel to user mode, and the processes with kernel level priorities achieved them in the sleep algorithm. User level priorities are below a threshold value. The kernel level priorities are above the threshold value. Kernel level priorities are further subdivided. Process with low kernel priority wake up on receiving a signal, but the process high level kernel priority continue to sleep. Next, a kernel calculates the priority of a process in a specific process states. It assigns a priority to a process about to go to sleep, correlating a fixed priority value with the reason for sleeping. The priority does not depend on the runtime characteristics of the characteristics of processes such as IO bound or CPU bound, but instead is a constant value that is hard coded for each call sleep dependent on the reason the process is sleeping. Processes that sleep in lower level algorithms tend to cause more systems bottlenecks. Longer they are inactive, hence they receive a higher priority than the processes that would cause favor system bottlenecks. For instance, a process sleeping and waiting for completion of disk has a higher priority than the process waiting for a free buffer for several reasons. So we'll see these reasons. That is first reason process waiting for completion of IO disk. Already disk IO already has a buffer. When it wakes up, there is a chance that it will do enough processing to release a buffer and possibly another resources. More resources it frees, the better the chance that the better chances are that other processes will not block waiting for resources. System will have a favor context switches and consequently process response time and the system throughput, that is output, are better. Second reason, a process waiting for a free buffer, a process waiting for free buffer may be waiting for a buffer held by process waiting for completion of IO. When the IO completes, both processes wake up because they sleep on the same address. If the process waiting for a buffer were to run first, it would sleep again anyway until the other process frees the buffer. Hence, priority is lower. The kernel adjusts the priority of process that return from the kernel mode to user mode. The process may have previously entered to the sleep state, may have previously entered the sleep state, changing its priority to kernel level priority. The process may have previously entered the sleep state, changing its priority to a kernel level priority that must be lowered to user level priority when returning to user mode. Also, kernel pages the executing process in fairness to other processes since it had just used valuable kernel resources. The clock handler adjusts the priorities of all processes in user mode at 1 second intervals on system 5 and causes the kernel to go through the scheduling algorithm to prevent a process from monopolizing use of the CPU. The clock may interrupt process several times during its time quantum. At every clock interrupt, the clock handler increments the in the process table on that process table and that records the recent CPU uses to the process. Once a second, the clock handler also manages the recent CPU uses of each process according to decay function. So decay is equal to CPU is equal to CPU divided by on system 5 when it recomputes recent CPU uses. The clock handler also recalculates the priority of process in the preempted but ready to run state according to the formula. That formula is priority is equal to recent CPU uses divided by 2, that is half of the recent CPU uses plus base level user priority. So where level user priority is the threshold priority between kernel and user mode, which is we have seen in the previous figure. A numerically low value implies high scheduling priority. Examining the functions for recomputation of recent CPU uses and process priority, the slower the decay rate for recent CPU uses, the longer it will take for the priority of a process to reach its base level. Consequently, processes in the ready to run state will tend to occupy more priority levels. See the movement of process on priority queues. See in this figure at user level, we have seen that in previous figure at user level there is only one process is at user level 1 there are 4 processes. So out of them one process moves from level 1 to level 0, that is movement of process on priority queues. So in a real system all processes with user level In real system, all processes with user level priorities in the figure would change priority queues, but only one has here we have shown in this figure. The kernel does not change the priority of processes in the kernel mode, nor does allow processes with user level priority to cross the threshold and attain kernel level priorities unless they make the system call and go to the sleep. Here, see this figure of process scheduling. See this figure carefully. See in this figure, there are three processes, process A, process B and process C are going to execute. The highest priority of executing process A, then middle priority is process B, and lowest priority of process C we are considering here. So time execution, these are the time slots. So these time slots are here. Each process have given 60 seconds to execute. So process A first executes 60 seconds. After 60 seconds, it time slot time slice goes to the process B. But while executing a process A, see here, process B CPU count is equal to 0. Process C also CPU count is equal to 0. So remaining time for this is a 30. That is a C allocated time for CPU count divided by 2. So 60 divided by 2, that is 30. Then here next 60 minutes 60 seconds time is given to the process B. So here at that time, process while executing process B, process C CPU count is 0. Here base time is 30. At that time, here time delay of CPU is reduced, total 30 divided by 2, that is 15. Here time slice for process B becomes 60 divided by 2, that is 30, and this time slice goes to the next 60 seconds goes to the process C execution, and time delay is 30 seconds. So at that next time it starts execution from next slot for process A. Then here it executes up to 67, from 70 to 67, because here difference of 7 minutes. Here initially difference is 30 seconds after execution of process A. After execution of process B, delay time is 15 seconds. After execution of process C, delay time is 7 seconds. So it executes from 7. So it executes a total 67, and delay time is 67 divided by 2 is 33. Then goes to the execution of process B and process C, so on. This is a process scheduling. So this figure shows the scheduling priorities on the system 5 of three processes A, B, C under the following assumptions. They are created simultaneously with initial priority 60. The highest user level priority is 60. Clock interrupts the system 60 times a second. The process make there is no system call and no other processes are ready to run. So kernel calculates the decay time of the CPU uses by this formula, that is CPU is equal to decay of CPU, that is equal to CPU divided by 2, and process priority is equal to CPU divided by 2 plus 60. So assuming that process A is the first to run, that it has highest priority, that it starts running at the beginning of the time quantum, runs for a second. During that time, clock interrupts the system 60 times, and interrupt handler increments CPU uses field of process A 60 times, that is up to 60. The kernel forces the context switch at a second mark, and after recalculating the priorities of all processes, schedules the process B for execution. The clock handler increments the CPU uses of process B 60 times during next, and then recalculates the CPU uses all priorities forces all the processes, and the forces a context switch. The pattern repeats with the process taking turns to execute. See here in this figure, first a time calculate is given 60 seconds. After that, CPU decay time divided by 2 is 30. Then after execution, process divide the CPU decay time 30 divided by 2, that is a 15. Then here 15. After execution, process C, so calculate this 15 plus 60, it becomes 75. So from 0 to 1, its delay time is 75. Then after executing process C, it divides by 2, it becomes as 7. So from 60 to execution, it becomes 67, and so on. So the pattern repeats until the process taking turns to execute. Then this is the round robin scheduling and process priorities. Suppose there are two processes process A and process B. So A is the highest priority for execution and B is the lowest priority. See in this figure for execution, in figure A, process A is entered for execution. After some time, process B is entered. See in figure B. So both processes are, so the kernel may preempt a process A, leaving it in the state ready to run after it had received several time quantum for succession of the on the CPU, and its user level priority may therefore be low as in figure A. As time progresses, process B may enter the ready to run state and its user level priority may be higher than that of process A at that, as shown in the figure B. If the kernel does not schedule either process for a while, both processes could eventually be at same user priority level, although process B would probably enter the level first since its starting level was originally closer to process C and process D. So after sometimes it both processes reach at same level, but the highest priority of execution is the process A. So process A executes first, then process B executes. Then next part, this is the example of process scheduling. A process must do the context switch when it goes to the sleep or exit. It has the opportunity to do a context switch when returning the user mode from the kernel mode. The kernel preempts a process about to return user mode if a process with higher priority is ready to run. Such a process exits if the kernel cannot a process with higher priority than the currently running process, or if the clock handler changed the priority of all ready to run processes. In the first case, the current process should not run in user mode given that the higher priority kernel mode process is available. In second case, the clock handler decides that the process used up its time quantum, and since many processes had their priorities changed, the kernel does a context switch to reschedule. So we stop here. Next time we'll start controlling process of priorities. If you have any problem, any doubt, please ask. Otherwise, write roll number and leave the session.